So the first thing I would like to do is go to Jupyter Lab, in which I imported the optimization for the resistive source with SLiCAP. And you see the model in SLiCAP. This is the figure. So this is the symbol for, you see the symbol in entry 19 here. It is just a symbol with a V and an I, and the parameters that I put in. And here I have put IG, the gate current, to 0, and some drain current and width that are matching on critical inversion. And the source resistance is 600 ohm, and the noise of the source resistance is included in the source. That is what it says. The noise is 4kT RS. So this is the schematic that is required. That's the only thing we need. And now we can play with W and L and the current to obtain the noise performance and see if there is an optimum. But first, maybe some instructions how it works. You always import SLiCAP first. That's important. I want to know the time because I always want to check if this version is faster or slower than the MATLAB version. So that's only interesting for me, but maybe you just copy it, you leave it in as well. Then you create a project that will check all the libraries and load the libraries and have everything available for you. If you don't do a project file, start a project, it will not know the libraries where to find it, and you get all kind of errors. I just defined a file name to that I don't have to repeat it, but I used it only one time, so it wasn't necessary. And I define an instruction. Circuit is an attribute of an instruction. So I set the attribute by checking it and just adding it to the circuit. And that is what the instruction set circuit file name does. And that is completely including the file extension .ser. That is different from the MATLAB version. You don't do .ser. There's a special set of instructions related to the Jupyter notebook. And one of those instructions is just with capitals SVG. Another one is with capital HTML. So if you do so, it immediately places the figure here in the environment, in a notebook environment. And you see, you do image to HTML, which is also in your own HTML directory where you create your output. You find the output here, and you can open this page. Open in a new. I think I have to do just open. No, I don't have to do just open. It's always what I worry. Do I have to do open or a new browser tab? Or I do a new browser tab because it's like this output. Okay. So this is for our own HTML file that you are going to check, this image to HTML and netlist to HTML that you are going to deliver us. But then for the capacitive source, you're going to zip this whole directory, including CSS, figures, images, etc. If you zip the whole HTML directory, we'll have everything and we don't need to run your file. That's the idea. So you can put comment in it, but you can also put LTSpice schematics in it as a figure and also plots as a figure that you import with image to HTML. 800 means that the width is 800 pixels and it scales width and height proportionally. So netlist to HTML, here's the netlist. I didn't generate it with LTSpice, but with another program. This is an old example. I also used Gschem for this. So that's why you see another netlist. And this is basically the circuit, the expanded netlist that is listed by SLiCAP. So these are the devices, the current controlled current source, a voltage controlled current source, a current control voltage source, sorry, copying the current of the noise source into a current, and this copying it into a voltage. And the gain of this source, of course, is, let's say, you see S divided by 2 pi ft. The gain is the D, and here is B. So that is the thing. And then the original current source, you see it here. And this parameter Rn is a kind of noise resistance. It is derived from the uh, from the uh, from the model, from the EQV model. Source resistance and source voltage, and that's the whole list. Because I want to do this exercise without 1 over F noise, I put this parameter KF, but it's a property of the N18 process, to 0. In a MATLAB file, you won't have this underscore because KF is just KF. I didn't make this two libraries. Then I'm setting the value, I'm getting the critical value, and I'm making the drain current so that it becomes the critical drain current. And that's what I do here with define parameter and get the value of the critical inversion coefficient. You could see that, by the way, if you would enter here, also, let's do that, because then you will see it live. I'm always a little bit scary of live because you can make easily HTML mistakes, and then you have the demonstration effect, yes. Params to HTML, and in MATLAB you just do like this, but in Python you have to do a little bit more, because Python is prepared of dealing with multiple circuits during one simulation, and MATLAB version is not. So here we do I1, which was the instruction, dot circuit. Then it knows that I need these parameters. I didn't run anything until now, so I need to run step by step. I can do this. Let's say Control Enter, it runs the thing, Control Enter, and then it will plot the whole thing. Less than 2 connections, no out is a warning, but that's not a problem. Netlist to HTML, then it gives you the netlist, and then para element data to HTML will give you this, and params to HTML will give you all the parameters that I just added, all the parameters that are from the EQV model. So if you're really interested in readable formulas of this noise model, then you can do this. And here you can see the critical inversion coefficient for this device with this length is 31.71, and the inversion coefficient at which is it now it is operating is almost critical inversion, 0.61, so that is okay. The noise resistance in this operating point is like 1 over GM, I told you, is about 52 ohm. So that also tells you have about 52 ohms on 600 ohm. That is telling you something about the noise. So you can use these parameters to understand a little bit the output of the complete thing. Here I already did params to HTML, you see, but I did it after I have redefined the current. And if I do it after I have redefined the current, so let's run this all again because that's necessary. I have redefined the current to be the critical inversion. So it wasn't at critical inversion when I started, but now it will be at critical inversion. And you see now it operates exactly at critical inversion. So my first guess wasn't good enough, and now it is exactly operating. And that's what I did, but with scaling the current with these instructions. Okay, this is just for the sake of showing you or having them available, RN, RS, FT, GM, and you can put them on the page if you want these parameters, or display them or whatever. So if I have this, and I would introduce a new field here, and I would say RN, then it will give me the value of RN. And if you do FT, then it gives me the value of FT. It's not very convenient the way of reading this. Then you have to format it as a float, as if you would do with Python in a normal way. So source, detector, etc. This is not necessary. ini.maxima. It's just like there was an old thing like you could also use another core, but this is just for testing purposes. It was there, so you can throw it out. So, and the plot instructions for the Python version are a little bit different. We have only plot sweep and a plot pole zero. There's a scatter plot and a sweep plot. And the pole zero plot is a scatter plot and the other plot is a sweep plot. If you want to know about all this stuff, you enter a field below. You type help with capital H as a function, and that should open the help file in your in the browser. Here it is a new browser, and here you can see the user guide and the whole reference. The whole reference is like if you are looking for plot, well, it's quite logical, but here SLiCAP plots.py, and then you find all the definition of the and the use of plot. And this is so the description, what the variable. Here you have a plot instruction. You have your plot pz, and probably there will be a plot sweep. Here you see all the fields you can enter with plot sweep, and they are explained here in this list. So the help file is quite, I think it's good enough. I use it myself because although I have written the program, I often forgot what I have been doing. Must be the age, I guess. So here you see the spectrum of the noise. And as we expect, we have this gate-induced noise, and you see the gate-induced noise is here increasing from about, let's say, about 5 gigahertz. It starts to play a role. So if I include 5 gigahertz in my frequency range, then maybe this is an optimum situation, but otherwise I may need another optimum value for the width. So here you can plot the numeric noise analysis, the formulas, all the contributions, and the noise figure. You can calculate the noise figure from the total noise, and the total noise is something I defined here. The total noise is RMS noise. It's the same instruction as it is in MATLAB. Noise result, that was the simulation result from, and I want to have it from the input, 1 gigahertz to 5 gigahertz. If you change these numbers or make it variables and assign them later on, then you get another value, of course. And the total contribution from the source in this input noise is the same, RMS noise, but now you say source is noise result dot source. So here it is, in fact, source is all, which is default, and here we have noise result dot source. So then the noise figure is 20 times the log of this RMS value, ratio of the two RMS values. So the total noise divided by the noise contribution of the source. And since log in SPICE means the natural logarithm, you have to divide by log 10. Otherwise, you have a wrong answer. And then it gives you the noise figure, and it says here 0.65 dB. So now we are going to do something. We are going to define the parameter width, and we are going to make the current change with the width, and we are going to maintain we change the width and the current, so we maintain the inversion coefficient. So I define a symbol W, and I delete the parameter width that I had before because it was already defined in my circuit. So, and then I define the current as the current that it was, the old value that I obtained by get parameter value, times W, which is the new parameter, divided by width, which was also the old value that I obtained somewhere, I don't know, here. Get parameter value W. So now the whole thing is scaled. And I can, again, calculate the noise, but now I have the expression in it with the width. I can also define the borders of the integration and keep them here in my expression. So So if I do symbolic simulation, or if I calculate it, f min and f max will just be part of the expression. So then I can calculate the noise figure as a function of the width. And of course, I can just solve this equation by differentiating it, the noise figure, with respect to the width, and then solve it for the width, which means I have differentiated and say the differentiation result should be 0 for, and then give me the width. So and then I find maybe the optimum value. So if you have complex values, then there's something wrong, or imaginary values, I mean, then probably you have a showstopper. It doesn't fit. So I'm only checking for positive values of the result. And here you see the result displays here, print W, that is my result, 47 micrometers. And here, if you want to see, there's indeed the whole equation available of the noise figure. You see the noise figure as a function of the width. And I see here in this equation that I could simplify it further because I see a few terms that are equal. This term is equal to this term, but it's really a difficult task to control the, and this long term here is also equal to this long term. So I could simplify it in f squared cube max minus min times this term, but then you have to map it on a kind of pattern. I didn't do this. I wouldn't know how in symbolic Python, but it must be possible. But if you simplify it in another way, let's say you expand the expression instead of simplify, expand, then you get, now I must do everything, otherwise I didn't run it. Then it displays it in another way. Oh, it's already there. Where I was. Here. You see, now it is completely in another way. And now if I do simplify, it makes a non-complex fraction. So only one fraction. Simplify. And if I do now this one, you get this. There are other ways, like you can try to factor it. Factor. Oh, I think there's something missing, yeah. And then it does this. So it's really to get an expression in the form you would like to have is not always easy. You really have to then dive into the expression and let's say resolve it term by term. Simplify. For me, this at the moment is the best. So the noise figure of the, and here I have some, I can make the expression a little bit more simple by including, of course, numerical values for the frequency range. So I'm going to substitute. This is just Python. Yeah, this is a SymPy object, and a SymPy object you can substitute. So this is just Python. That's why it's good to know about Python and SymPy. SP SymPy is included in SLiCAP. So sp.latex is make LaTeX of this, put it between two $signs, because then the instruction HTML will nicely display it in LaTeX. Round N means round it to, and that is in the settings, to 4 digits. And you can change the digits in the settings of the program. So now I'm going to create a plot, and this is really nice. You can, in MATLAB, you needed to make a kind of parametric plot. That's why it takes much longer time. But here we just say, no, I have a formula. I just have a formula. I have the noise figure as a function of the frequency for a certain frequency, as a function of the width for a certain frequency range. So I can step it for different values of fmax, for example, and step it from 2 gigahertz to 10 gigahertz linearly, set, of course, a thing to numeric, and calculate everything and then plot it. And look, here you have a plot of the noise figure as a function of the maximum frequency and the width. The width is here along the x-axis, and the maximum frequency is a parameter along the curve. So you see, for example, the red one is the maximum frequency is 2 gigahertz. If the maximum frequency is 2 gigahertz, I can make the width much longer before the high frequency increase comes up. And you see, it appears that it, well, making it the fmax lower or making the width longer doesn't help anymore. This appears to be a showstopper value. So if someone asks you, can I do with fmin is 200 megahertz and fmax is 2 gigahertz, a noise figure of less than 0.2 dB? No, not in CMOS 18. Not in this CMOS 18 process. It's simply shown by this curve. But if you go to a higher frequency, then you have to make the device shorter. And making it shorter, narrower. The width should be less. So you have to make it narrower, which means GM will be a little bit less and the noise will be higher because the contribution of the gate-induced noise is much higher. And this is a plot that shows you how this works. So I hope I have explained more or less the way of doing this. And now I want to know, did I include something from LT-Spice? I think I didn't. No. And I did, I think, in the Python file. Did I do it in Python file? Yeah, in the Python file I did. So you also have this Python file, sorry. You also have this Python file. So I, this CS-.py, it creates the Bode plots. It lets you, oh yeah, I did it for the other stage. Yeah, I didn't do it for the noise, but this has already been done in the CS stage that I've given to you. Here you see, I create an HTML page, LT-Spice CS stage, some heading on it, the image. You see, this is created from the plot from the circuit of LT-Spice. You can also put PNG there. If you just make a screen dump and cut the pieces off that you don't want, save it as PNG, you can also make PNG. And here's so the image, the response. So this is how you can include LT-Spice results in your report from SLiCAP. So therefore, this reason you only have to deliver your HTML directory, and it should include everything.